Good day, everyone. The topic that we will be discussing today is about the algebraic functions. Before we proceed to the fundamental formulas in solving derivatives of algebraic function, first we must recall the basic concept of the uh, a derivative. So we know that a derivative in mathematics, it means a change. So if we have dy dx, so this is a derivative, or this is a first derivative. So in order to read this one, we could say that it means dy dx, it means or dy over dx, it means change in y with respect to the change in x, or sum of this is also the same as y prime. Okay, so again, a derivative, it means change in mathematics. So before we start the sum of the examples in algebraic function, first we are going to enumerate what could be or what are the fundamental formulas in solving the derivatives of algebraic functions. So first formula that is really applicable in terms of algebraic function, this is the derivative of constant. So if we have so the formula for it, or the equation or the theorem, is that the derivative of constant, any constant with respect to x, automatic equal to 0. Okay, so later we are going to discuss one of the examples. And then in the product rule, uh, uh, the derivative of u raised to n over dx, the formula for it is n u, wherein our u is a function, u raised to n minus 1, and then dx. Okay, sorry. So our formula for the power rule is the derivative of u raised to n over x, or with respect to x, equals n, which is our n here is the exponent of the u, the same u, and then n minus 1. So that is the formula for the um, uh, power rule. So the constant multiple rule is that these are such functions wherein it has a constant or a coefficient. So that the third one is about constant multiple rule. So the concept here is just it has a coefficient or it has a constant. So the formula is so the derivative of c. So here it is. So the derivative of c times any function with respect to x is equals to c times the first derivative of the said function. So it means what, in order for it to solve, is just separate the constant. So our c here is constant, so the same also here. So just separate the c, or put it in the outside, and then before you are going to derive this said function. So the fourth one is the sum of functions. So for example, if we have a functions u, u and then v. So if we're going to, or u plus v, so if we're going to find or the theorem for the derivative of sum of functions is that uh, the derivative of u plus v with respect to x, this is equals to the derivative of u with respect to x plus the derivative of b with respect to x. Then also we have also the derivative of difference of functions. So the concept is just the same with the sum of functions. The only comparison is that this sign or the operation. So at this point, if we have the derivative of u minus v with respect to x, so it means that we have uh, the derivative of u with respect to x minus the derivative of v with respect to x. It means that uh, you will you will derive them separately. So first we're going to derive the u function with respect to x, and then the second one is the v function with respect to x. So the same also. So the sum of functions and difference of functions, they are just the same in the concept as you observe, but the main comparison is that the only is it's about the operation. So the next one is about power rule. I know product rule. So if we have a product, so let's say the product of 2 u times v. So at this point, if we are going to based on the theorem of the product rule, is that the derivative of two functions, so our functions is u and v, so with respect to x, so this is equals to u times the derivative of v with respect to x plus v the derivative of u with respect to x. So this is the formula for the product of two functions. So the derivative. So if we have u times v, all we need to do is just copy the u and then multiply to the first derivative of v divided by x plus then copy the v, then multiply it to the derivative of u with respect to x. So that's it. So the last one is about the quotient rule. So the quotient rule, if we have a u divided by v, so if this is our equation or our function, so this is, so our functions here is u and v, so the derivative of two functions wherein they are in quotient or at quotient, so to so the theorem for the quotient rule is that the derivative of u divided by v with respect to x, this is equals to um, so let's proceed here. So this is the derivative of the, so the derivative of u divided by v is v du dx minus u dv dx over v squared. So this is the equivalent. So when you are deriving two function wherein the operation is division, or u divided by v, this is the function, what you need to do is, so we know that the u is the numerator and then v is the denominator. So always here is the v, so this is always v du dx, so v the derivative, so times the derivative of u over dx minus, and then the numerator u times the derivative of v with respect to x over the square of the denominator function. So now let's try some examples. Now our first example is about the derivative of constant. So for example, if we are going to solve for, so our function is, so let's say y is equals to 8 pi, 8 plus pi, and then the second equation is y is equals to 600, then 3 y is equals to e raised to 5. So if this is our function y, so the first one, so we know that again is, so if we are going to derive such constant, so the derivative of any constant with respect to x, it is automatic to 0. So we could say that the derivative of the dy dx of our first example, its derivative is automatic 0 because it is a constant and also pi is a constant. So the same also with our second function, y is equals to 600, automatic that our derivative with respect to x or our y prime, this is automatic 0 because 600 is a constant. And also, with regards to the third function, y is equals to e raised to 5, if you're going to find the first derivative or the derivative, so dy dx or the derivative of e raised to 5 with respect to x or our y prime, automatic this is equal to 0 because that is based on the theorem of the derivative of constant. Our next example is about some of the examples in terms of power rule or any functions that it has exponent. So again, as a review, that we know that in power rule, in order to derive or to differentiate such function is, so if we have a function of y, we could say that the derivative of y with respect to x, we know that, or so this is the first derivative. Oh, so if we have function of so if our function is y is equals to x raised to n, so we could say that the derivative of x raised to n, so based on the theorem of the power rule, with respect to x, this is automatic. So x is the part of the function. So n the exponent, and x raised to n minus 1. So we could be able to use this one. So if we're going to find some examples, so if we have y function natin is y is equals to x raised to 5. So if we're going to find the derivative, so we can say that dy over dx, or the derivative of x raised to 5 with respect to x. So we could be able to use this. Our the theorem is, we know that uh, the n is our exponent. So what we need to do is just bring down the exponent. So exponent natin is 5. So just bring down the 5 and then copy the x. And then exponent minus 1. So our exponent is 5 minus 1. So therefore, our answer is 5x raised to 4. So this is already the answer. So we could say that y is equals to x raised to 5. The first derivative of x raised to 5 with respect to x is 5x raised to 4. Or dy dx or y prime, so they are just the same. Y prime or dy dx, this is equal to 5x raised to 4. So, next example. So how about if we have this kind of, so y is equals to x raised to 6. So the same concept, if you're going to find for the derivative with respect to x, again, just take note with the exponent because this is power rule and we are involving with power or the exponent itself. So just based on, just focus on our theorem or this kind of that 6 is our n or our exponent. So just bring down the 6, then copy the x, and then 6 minus 1. So that's based on our theorem. So automatic, this is equals to 6x raised to 5. So therefore, the first derivative of y, wherein our y is equals to 6 raised to 6, x raised to 6. So our derivative is 6x raised to 5. So how about if we have our y is equals to, say, w raised to 5. So we know, so if we're going to derive this one, so at this time, we are, so dy dx, so no, this is now a wrong interpretation. As of this moment, we are not in terms of x anymore because we are deriving such function with respect to w. So we are going to solve the derivative of y with respect to w. So w. So the same concept. So the main difference lang is that our, instead of x, we are going to use the w. So w, so the same concept. So n, this is 5, and then w, and then n minus 1 raised to n minus 1. So 5 minus 1. So therefore, our answer is 5w raised to 4. So just uh just a reminder for everyone that not all the time that you are going to derive such function always in terms of x or with respect to x. So not all the time. So it depends on a particular function. So in our first problem, our function is y. So we derive this one in terms of x because the x here is involved. So but in the second one also, so this is x raised to 6. So we derive a function with respect to x. So in our third example, this is there is a main difference that we are deriving the function, the derivative of y. We are involving now with w. So the derivative of y with respect to w. And also if we have last example, so if we have y is equals to, or no, let's try naman. So if we have v is equals to um t squared, t raised to 3. So we are going to find for the v prime. So our v prime here is also equal to the derivative of v with respect to t. Okay, so in here, if we're going to find the derivative of, so this is y, right? So this is also equal to our y prime, wherein y prime natin is with respect to w. So ito naman, dv with respect to dt, because we are deriving the v, or our function v, so with respect to t. So automatic our dv with respect to t is equals to, bring down the exponent 3, t raised to 3 minus 1. So automatic 3, copy the 3, so t raised to 2. So this is our answer. Now, our next example is about a constant multiple rule. So we know that again that in this theorem, if so, it only involves the about coefficients or constant that are attached or that are with the function. So for example, if so again, so let's try to put the derivative of c times our function. So let's say our function is y with respect to x. So automatic, what we are going to do is c, just separate the c, and then we derive now the function. So it goes like that. So that is how. So for example, so at this point, if we have this kind of example, so let's say if we have a y is equals to 5x raised to 3. So this is now under the constant multiple rule. So we have a constant, or our coefficient is 5. So y equals 5. Then separate the, then so let's find now the derivative of y with respect to x. So let's separate the 5, and then we are going now to solve for, so this is under the power rule, wherein again that the derivative of x raised to n with respect to x is equals to nx raised to n minus 1, right? So at this point we can say that this is 3, bring down the 3 exponent, x raised to 3 minus 1. So this one. So automatic, overall we could say that our derivative with respect to x, this is equals to 5 times 3x raised to 2. Overall, the derivative of y with respect to x to find our final answer, so this is also equal to y prime. This is equals to 15x raised to 2. So this is now our final answer. Also, so if we have an example, say y is equals to 5t raised to 4. So to find the derivative, so with respect to t, so what we need to do is just separate the coefficient or the constant that is there, and then bring down the 4. So now we can apply now the derivative of t raised to 4. So we can now apply 4, bring down 4, and then t raised to 4 minus 1. So overall, this is 5 times 4t raised to 3 plus 4 minus 1 is 3, and then also this is equal to 20t raised to 3. So this is our answer.